to discuss second order perturbation theory, though you should note that really I'll only cover the energy rather than the changes to the wave function. I will mention them, but not in detail. So we start with the second order perturbation theory equation. So we have H prime acting on psi n of 1 plus H0 acting on psi n 2. That's the left-hand side. Notice that the left-hand side always only ever has two terms. That's because there are only two terms that can ever contribute. The right-hand side will have a number of terms equivalent to the number of ways of making the order. So if it's second order, then you can make the second order perturbation, you can make 2 from 0 and 2, 1 and 1, or 2 and 0. There should be 3 terms. And indeed there are. We have En of 0 psi n 2 plus En 1 psi n 1 plus, and then the final term is En 2 psi n of 0. Okay, so from here we want initially to find E2, En of 2. So we're going to contract, as usual, with bra psi n 0. That's because that will take this term here, the final term on the right hand side, and give us just an En2. We're also going to substitute in for psi n of 1. Substitute for ket psi n 1. Okay, so when we do that, what do we get? Well, we get bra psi n 0, then we get H prime, that's our perturbation, and then we get a sum over k of a nk of 1 acting on ket psi k of 1. That's the first term, of 0. That's the first term. The second term gives us bra psi n of 0, an H0 and a psi n 2, and that's going to equal En of 0. We're going to have bra psi n of 0 ket psi n of 2 plus En 1. We're going to have bra of psi n of 0, and then we're going to have a sum over k of a n k 1 ket psi k of 0, and then at the end we're going to have En of 2, because the final term on the right hand side gives us En of 2, because psi n is 1. I want to emphasize again that psi n2 and psi n1 are simply corrections to the starting wave function, so they do not form a basis set, and we cannot assume anything about their properties. So we can't assume that they're orthonormal to each other or to psi n of 0. We have to evaluate those matrix elements. Now we need to simplify. What we're going to do, so the second term on the left hand side, psi n0 h hat psi n2, is equal to the first term on the right hand side, En0 psi n0 psi n2, for exactly the same reason that we saw in the first order perturbation theory. So we're going to cancel these two terms. I'm going to take excuse me, I'm going to take the psi n0 and the h prime inside the sum in the first term on the left hand side, and on the right hand side I'm going to take the psi n0 into the sum. So we're going to end up with the following equation. We have sum over k of a nk of 1, and then we're going to have bra psi n 0, we're going to have a h prime, we're going to have ket psi k of 0. And that's going to equal En of 1. And then we have a sum over k of a n k of 1. Sorry about the k there. And then we have bra psi n of 0 ket psi k of 0. That's going to turn into a delta function, obviously. Let's put the ket there. Plus En of 2. Right, we need to simplify that. So I'm going to write this term here on the left-hand side as just h prime n k. That's a fairly standard approach. And I'm going to rearrange things a little bit, so we now have that En of 2 is equal to the sum over k of a n k 1 h n k prime. And we're going to subtract off that En 1 a n n 1. Now that was the first term on the right hand side in the line above, so I'm just going to put a little arrow pointing to that, and what happened there was the psi n psi k becomes a delta nk, and therefore we pick up the only value of k where k is equal to n, i.e. a factor of a n n. Now if we're summing, if we now come back down to this final equation that I've written, what we're doing is we're summing over k, and we're getting an ank of 1 hnk prime, and we're subtracting off that en1 ann, but that actually cancels the situation in the sum where k equals n, so we just have the sum over k not equal to n of a nk of 1 h nk prime, which we can write as the sum over k not equal to n of h prime kn h prime nk. We can divide that by En of 0 minus ek of 0, and that's substituting in the value for ank of 1. Now what we have here is we have the product of two complex conjugates, so that of course can also be written as sum over k not equal to n of the square modulus of psi k of 0 h prime psi n of 0 divided by En of 0 minus ek of 0. Of course that's going to break down if En is equal to ek. At that point you have degenerate energy levels, and you need to use a technique called degenerate perturbation theory, which I will cover in another webcast. We're not going to derive this, but you should note that if you want to find psi n2, in other words the second order correction, then you do exactly what we did for the first order. We represent it as a sum over k of a nk 2 psi k 0, and you substitute that into the second order equation at the top. Let's label that as equation 1. So you substitute this into equation 1. You contract with a bra, so that's going to be bra psi L of 0, and you solve. And that's relatively easy to do. There's a little bit of mess keeping track of the different coefficients, but it's not a challenging thing. However, the approach of the second order perturbation theory gets more complicated, and we're not going to cover it in this course, but I thought you might like to see where we would go with that. And you can of course continue on to third and fourth and fifth order perturbation theories. You can find those in advanced quantum mechanics textbooks or in various places on the web. So we've now got the second order correction to the energy as an explicit formula. We discussed some of the properties of that in the lectures. We noticed, for instance, that as n and k become further apart, then the denominator, the bottom of that fraction, is going to become larger and larger, and so the contributions are generally likely to be smaller. Of course, that will depend on the magnitude of the matrix element. We also noticed that for the ground state, En minus Ek is always negative. The top, which is a square, is always positive. A square modulus, which is always positive. So the second order energy correction is always negative for the ground state. I hope that that derivation helps you see where the different formulae come from. There are various examples that we've done in class, and that's about what you need to know for perturbation theory.